Welcome back to the Deep Dive. This information is presented by Bluewater Auto Restoration, and this is your deep dive for week 47 of 2025.
Hard to believe we're already there.
I know, right? And just a reminder for everyone listening, we release these new deep dives every Saturday morning.
Bright and early.
Exactly. So today, we are immersing ourselves entirely in the world of composites, specifically how to repair, restore, and really properly finish those lightweight, yet, let's be honest, often temperamental body panels made of fiberglass.
That's absolutely right. I mean, fiberglass panels, you find them everywhere, right?
Yeah.
From classic Corvettes all the way to custom dune buggies. They offer incredible design freedom and weight advantages, definitely.
But they're different.
Oh, yeah. Repairing them requires a fundamentally different philosophy and a different skill set than working with, say, sheet metal. Our mission today really is to extract the essential high-value knowledge. We're talking specific techniques, the material chemistry involved, which is critical, and the crucial safety protocols, things you absolutely need to know to handle fiberglass effectively. We want to ensure not just structural integrity, but also, a truly flawless, long-lasting finish, one that won't show ghosting or cracking years down the road.
Yeah, nobody wants that. Okay, let's unpack this then. When we talk about fiberglass, or GRP, that's glass-reinforced plastic, we're talking about a composite. What exactly does that composite structure give us, maybe chemically, mechanically, that traditional steel just can't?
Right. Well, mechanically, the key word is composite. You're leveraging the best properties of two very distinct materials. You've got the woven glass fibers themselves.
Okay.
These provide tremendous tensile strength, basically. They resist being pulled apart.
Right.
And then you have the matrix, which is the resin, usually polyester, vinyl ester, or sometimes epoxy. That binds those fibers together, transfers the load between them, and it provides, the compressive strength and the actual shape.
So it's the combo.
Exactly. Fiberglass uses the high tensile strength of the glass and the bonding strength of the resin together. And this creates a material that's incredibly light, yet remarkably rigid, if it's laid up correctly. That's the key.
And its history in the auto world, it's pretty deep, isn't it? I mean, you look at the 1950s, the emergence of the Corvette is kind of the defining moment, right? Carrying that torch from the C1 right through to the C7 generation.
Absolutely the icon.
But its use quickly expanded beyond just, high-volume American sports cars, didn't it?
Oh, for sure. It really became the go-to material for innovation and niche manufacturing. Think about those lightweight European sports cars like Lotus, where minimizing weight was everything.
Yeah, Chapman's philosophy.
Exactly. And TDR, known for their really aggressive styling. Even the Studebaker Avanti back in the 60s showed it could be used for premium, design-forward production cars.
Right.
But where fiberglass really, really cemented its place was in those non-traditional applications. Things like custom truck hoods, massive spoilers, body kits.
Kit cars?
Oh, yeah. Definitely kit cars and recreational vehicles, like dune buggies. And the reason is pretty simple. The raw materials are accessible, and you can mold these really complex organic shapes far more affordably than, building a massive steel stamping facility.
Okay, so if it was cheaper to mold and significantly lighter, you mentioned up to 50% lighter than equivalent steel panels and completely corrosion-proof, why isn't every car body made of fiberglass today? What are the inherent disadvantages? What stopped its complete takeover?
That takes us directly to the crucial mechanical caveat: how it handles failure, how it breaks. Steel is ductile, right? It dents, it deforms, it absorbs impact energy across a pretty wide area.
And you can often push it back out.
Yeah, you can repair it by pushing the metal back into shape, hammering and dollying. Fiberglass, on the other hand, is brittle under sudden, sharp stress. When you hit its stress threshold, it fails abruptly. It cracks, it delaminates. Sometimes it just shatters.
Right, so a totally different repair mindset.
Fundamentally different. You aren't shaping. You are structurally rebuilding a specific area. You're basically gluing it back together, stronger.
Okay.
And beyond the brittleness, there are two major enemies, things that challenge its longevity if it's not properly protected. First is UV rays. Sunlight chemically degrades the resin matrix over time, causes chalking, weakening. And second is moisture infiltration, water getting in. That leads to internal structural problems like osmosis, blistering, and layer separation or delamination.
Got it.
And, crucially, achieving that maximum structural strength. It relies entirely on the precision of the layup process. You need the correct ratio of fiber to resin. Unlike steel, which is homogeneous, you can't just assume a fiberglass panel has uniform strength if the structure wasn't precisely engineered and laid up correctly in the first place.
Okay, that makes sense. So to repair fiberglass correctly, you almost need to be like a materials engineer, mixing and matching components. Let's start with the reinforcement, the actual glass fibers. Why can't we just use one type of fiber material for every single repair?
Yeah, good question. It's because every type of fiber reinforcement serves a different mechanical purpose. You have to select your material based on the load path you need to rebuild, the stresses it needs to handle.
Okay.
So the foundational material, the one most people think of, is chopped strand mat, or CSM.
Right, the messy stuff.
Yeah, it can be. It consists of random short fibers held together by a binder. When you add resin, that binder dissolves, and it allows the fibers to conform really easily to complex curves.
So it's good for shapes.
Exactly. CSM is essential for building bulk, filling voids, and creating those initial foundational layers because it wets out really easily. But it is inherently weak under tension because the fibers are short and they're not aligned in any specific direction.
Okay, so if CSM builds bulk but isn't strong in tension, what provides the actual structural muscle, the directional strength needed for, say, a panel edge or a mounting point?
Right? For real structural integrity and load-bearing applications, you must use woven cloth or woven roving. These are different. The fibers are interlaced in patterns, kind of like weaving a heavy fabric.
Okay, I can picture that.
And this provides significant, measurable directional strength. So, for instance, if you're repairing a cracked frame rail, which some cars had, or a high-stress mounting point for a bumper bracket,
Yeah.
woven cloth ensures that the load is distributed across those continuous fibers, running in specific directions.
And what if the panel is really large and needs massive rigidity? Thinking like a racing hood or maybe a long, flat fender that could flex?
That's where you start combining materials, or you move up to more advanced stuff. You might use biaxial or triaxial fabrics. These have fibers stitched together in multiple orientations, like 0 degrees, 45 degrees, 90 degrees, for maximum multi-directional strength.
Okay.
And for sheer rigidity, without adding a ton of weight, we often use core mat, or sometimes honeycomb core. This is a bulky, low-density material that you sandwich between two layers of woven fiberglass.
Like a structural sandwich.
Exactly. It functions just like an I-beam in construction. It separates the two fiberglass skins, which dramatically increases the panel's moment of inertia, its resistance to bending. This boosts stiffness and rigidity incredibly. It's pretty much mandatory for large, flat automotive panels to stop them from flexing or drumming, from wind or vibration at speed.
Yeah, you don't want your hood fluttering. Okay, finally, on the exterior, there's that first line of defense, gel coat. We often just think of it as the color layer, but its function is way more critical than just aesthetics, isn't it?
Oh, paramount. Absolutely critical. Gel coat is a specialized pigmented resin layer. Typically, it's polyester or maybe vinyl ester based, and it forms the outermost skin. Its critical function is UV protection.
Ah, okay.
It stops the sun's rays from penetrating and degrading the structural resin layers underneath. It also provides the gloss and that smooth, pore-free exterior finish. And importantly, it acts as the primary barrier against moisture infiltration, which, as we just discussed, is the precursor to nasty stuff like blistering and osmosis.
Okay, so gel coat is way more than just paint. Now, here's where it gets really interesting for me. The resin chemistry. This is the glue, the binder holding it all together. Let's talk about the three main players: polyester, vinyl ester, and epoxy. Why would a restorer choose one over the others, and what are the real-world practical consequences of that choice?
Yeah, this is crucial. It really boils down to a cost versus performance calculation, and that calculation has massive long-term implications for the quality and longevity of the finished product.
Okay.
So, polyester resin. This is the industry standard for general, non-critical fabrication and repair. Why? Because it's the most affordable and generally the easiest to work with. It cures relatively quickly.
But there's a catch.
There's always a catch. The practical consequence of its chemistry is its high shrinkage. Typically, polyester shrinks about 3 to 5% by volume as it cures.
3 to 5% doesn't sound like that much, but you mentioned earlier that shrinkage causes print-through, or ghosting, where you can see the fabric pattern through the paint later. So for a high-gloss finish on a critical panel, like a Corvette hood, are you basically saying polyester is almost a guaranteed route to seeing that weave pattern eventually? And maybe epoxy is the only professional solution to truly avoid that ghosting?
For a high-gloss, show-quality finish on a large critical panel,
Yeah.
yes, using polyester is a major risk for print-through. That 3-5% shrinkage, even though it sounds small, exerts internal tension within the cured laminate over months, maybe even years. It slowly pulls the resin matrix tighter around the fibers.
Ah, I see.
And eventually, this makes the woven cloth pattern subtly visible right through the paint layers. That's the ghosting effect. So, if structural integrity is secondary and cost is primary, okay, maybe polyester. But if the appearance and long-term stability are paramount, you really must upgrade the resin.
Okay, so what's the first step up?
That upgrade usually starts with vinyl ester resin. It sits in the middle. It provides improved chemical resistance compared to polyester. It's much less prone to hydrolysis, its water absorption, and it generally has better flexibility.
Flexibility. Why is that important?
Well, if a panel is subjected to continuous road vibration or minor stress, think of a front bumper. Maybe a wear flare vinyl ester handles that repeated flexing better without developing those internal micro cracks that polyester can be prone to. It's really an excellent middle ground. Better performance, still reasonably workable.
But if you're doing professional grade, really mission-critical repairs, especially on older fiberglass or structural stuff, the consensus seems to point squarely toward epoxy. Why? What makes it the top tier, especially that specific adhesion to existing fiberglass you mentioned?
Epoxy is generally considered superior for restoration work for two main reasons. First, it offers the absolute lowest shrinkage, usually less than 1%, so it virtually eliminates that risk of print-through or ghosting. That's huge for finish quality.
Okay, minimal shrinkage. What's the second reason?
Second, and this is critical for restoration, it provides the best chemical adhesion to existing old cured fiberglass. When you grind down old polyester or vinyl ester, sure, you create a mechanical key for the new resin to grab onto.
Right, like roughing it up.
Exactly. But epoxy goes beyond that. It creates a much stronger chemical bond across that interface. Using epoxy dramatically reduces the chance of bond failure where the new repair meets the old panel. It makes it far less likely to fail or delaminate under stress compared to a repair using polyester, which honestly can sometimes peel away from the old substrate over time if the prep wasn't perfect.
Okay, that makes a strong case for epoxy, especially for valuable panels. Now let's talk chemistry in practice. The catalysts or hardeners. For polyester and